Okay, good morning, everyone. This is day 3 of our summer school, and welcome back. I know there's people from across the globe, so good afternoon, good evening, and well, hopefully not quite good night yet. Thank you all for staying at it, and today we have an exciting lineup of talks on applications of artificial intelligence, machine learning, and deep learning to the earth and environmental sciences. The last couple of days, you've been exposed to a solid set of talks and exercises on the fundamentals of machine learning and deep learning. And today you'll get to see how these are used in operation, in research, as well as in actual operation for various different applications in weather and climate and in Earth system models. I'd like to, first of all, introduce our first speaker, which is Dr. Sue Helen Haupt. Dr. Haupt is an NCAR senior scientist and a deputy director of the Research Applications Laboratory at NCAR. She's also a fellow of the American Meteorological Society and one of the early pioneers of the applications of AI in the environmental sciences. So thank you, Dr. Haupt, for joining us today, and over to you.
Okay, thank you for the nice introduction, Karthik. Today, I'm talking about machine learning in weather forecasting systems. Over the last couple days, you learned a lot about machine learning, but how are they used? How can we use them to really make improvements in what we do and in weather and climate systems? And that's my goal today. We're going to start by talking about why are we using AI machine learning as part of weather forecasting. We'll talk a little bit about the nature of weather and how we've traditionally done some weather forecasting and where we can begin to use AI machine learning in weather forecasting. Then we'll move to some specific applications. One of the biggest uses for machine learning is in post-processing of numerical weather prediction systems. We'll look at how we can use a systems approach to blend the best of the physics that comes with the MWP with the machine learning, and give some examples from renewable energy forecasting, forecasting for severe weather, forecasting for wildland fire prediction, and then we'll look at how we can use machine learning in parameterizing the models better themselves. So first, I'm going to talk a little bit about history and philosophy of how we think about weather forecasting. If you go back to ancient man, as people began to observe the sky, they noticed patterns in the sky and came up with maxims. Things like red at night, sailors delight, red in the morning, sailors take warning. And although they didn't understand what was happening, they didn't really get the fact that there's selectively scattering those long red wavelengths, so that when the systems are coming from the west, when we have clear weather systems, the larger dust particles are scattering those red light waves. They were able to still observe the historical information and make these generalizations. Now, when you think of it, that's often what we do with machine learning. But in this case, it's been really human learning of the patterns. Now, we've known these sorts of things. We've been doing them for at least 2 millennia. You know, even a biblical reference, it will be fair weather, for the sky is red in the morning. Today it will be stormy, for the sky is red and overcast. So it's not new. It really has been done for quite a long part of time. Now, people evolved in how they looked at weather. They began to look at patterns in the weather. They began to understand that there's cold fronts, warm fronts, low pressure systems, high pressure systems, the fact that the low pressure is associated with stormier conditions, high pressure, very clear. About 100 years ago, the Bjerknes were able to come up with the Norwegian cyclone model. That classification, again, it came from long observations and trying to understand the patterns in the weather. Okay, then we moved toward a more reductionist approach, starting from first principles. And you know, those of us who study weather forecasting began learning the physics, conservation of mass, momentum, and energy, talking about parcels and these conservation, writing the Navier-Stokes equations, discretizing those equations, adding parameterizations. That led to numerical forecasting. L.F. Richardson was the pioneer, again, about 100 years ago. He was able to talk about and visualize a hall, a gallery with lots of computers around. But in that sense, his computers were people with slide rules, doing computations, passing information back and forth. And from the tall pit, a tall pillar in the hall carried a lamp. And when one area was going too fast, they would shine a red light. Another area was going too slow, a blue light. And he visualized what we have known now as modern computing with multiprocessors. Now, it wasn't until we led to the rise of modern computing, and of course, everybody knows the ENIAC, developed in around 1946. The first big problem accomplished was numerical weather prediction. Now, unlike L.F. Richardson, Charney, who led the team that did this, filtered the equations and was able to produce the first NWP forecast by having information. Okay, then people began to think that all we have to do is build bigger computers, discretize smaller, and we'll be able to predict the weather perfectly. But then along came Lorenz and a re-recognition of sensitivity to initial conditions, the fact that we have a chaotic, nonlinear dynamic flow leads to limits of predictability, very sensitive to initial condition. So then we began to think of weather in terms of attractors and manifolds, where we need to use data assimilation and initialization to get the best possible initial condition. We also started to think in terms of statistical forecasting being a way forward, ensemble forecasts so that we can quantify the uncertainty due to this lack of predictability, building empirical models, and post-processing. And AI became a part of all of those. So that has really led to a change in how we think about forecasts and really led to an opening to go back to observations, data, and really have two approaches to weather forecasting. One is the equation-based, the numerical weather prediction with pre and post-processing. And the second, of course, is empirically based. Begin with data and look for the patterns. That has become the artificial intelligence, the machine learning piece, repeating what those early humans did, noticing patterns, but in this time, codifying it using our machine learning techniques. And for the best applications, we can blend these two approaches to optimize our prediction. So now we're blending observations, models, AI, new methods have emerged to bring that observed data. It really is an original Internet of Things. We have real-time data coming in, blending in the gridded model output, where we have the numerical weather prediction models, many of them being run faster than real time, so we can use the information, combine that with our increases in computer power, then bring in the AI machine learning methods. Then we can leverage and offer alternative approaches to just traditional NWP using big data approaches and coming up with ways to model this complex Earth system. Okay, now we'll talk a little bit about specifics. How have we used AI and machine learning in weather forecasting? Well, at NCAR, the first big AI success was building Diecast, the Dynamic Integrated Forecast System. Diecast uses output from the numerical weather prediction models, brings in observations, has a historical record of the two, blends them in smart ways, and makes predictions of weather variables. So it generally is a machine learning post-processor of the model data that learns the predictive relationships between the model output and the observations. Then we can optimize the desired forecast variables. We can combine multiple NWP model outputs. It enables real-time decision support using real-time data, again, Internet of Things, and large amounts of data. So we use both real-time data as well as having case histories, historical data for the training of these models. Now, Diecast was started in around 1999 at what was then the Research Applications Program of NCAR, originally commissioned by the Weather Channel. When they decided they were going to make international forecasts, they realized that it was no longer possible for their human forecasters to be able to make forecasts for every city around the world. They wanted an automated system to produce their public-oriented forecasts. They came to NCAR and worked with NCAR to develop the system. Originally, we had scientists like Peter Neely and Bill Myers working on this. Now it's used in many other projects as the weather engine. It's being used for surface transportation prediction, bringing in information from connected vehicles real time, blending that with weather forecasts, with observations from satellite radar in the region, allocating those to road segments so the traveling public has information. It's being used in solar energy prediction, wind energy prediction. I'll talk more in detail about these two applications, as well as precision agriculture. There are various commercial forecasting companies using Diecast as their engine, and when they enter forecasting contests, typically the companies with Diecast do quite well, even though it now is a 20-year-old system. So how does Diecast work? Okay, starts with measurements. These measurements from the field, real-time observations, trained with historical observations. Also have input from various models. Oftentimes, the NOAA models, high resolution rapid refresh, as well as global forecast system, often use other models. The Canadian GEM model sometimes include the European ECMWF. What other model output? We often run a customized version of a model, such as the weather research and forecasting model for particular applications. And in recent years, we've been blending in very specific machine learning models. Now, each of these models has its biases, and we're able to apply model output statistics, such as very similar to the way Bob Glahn developed MOS back in the 70s, but now it's done dynamically on each of these models, optimizing the output for each of these models according to prediction time, lead time, time of day, etc., for the forecast variables that we care about, but using a host of other variables. So the dynamic MOS corrections then are combined optimally in an integrator. So the integrator does an optimal weighting, again, specific for the particular time. One of the keys to diecast success is that the weights for this integrator are dynamic as well, and they can be updated on a regular basis. Now, after a little bit of post-processing, then the output is often multiple weather variables. We currently have a host of software engineers in the research application lab working on this, led by Jim Cowie, Seth Linden, Bill Petsky, Ishita Srivastava. Now, when we apply diecast, for instance, to wind energy problems, we need observations in the field. And for wind energy, we actually use wind measurements from the nacelle anemometer on top of the wind turbine. And when we apply it to wind energy, we find that the error in diecast, the solid black line here, compared to the dynamic MOS corrected versions of all the input models, and the RMSE by design, on average, will be lower than the best model after the DMOS has been applied. And in fact, for wind speed, we often find on the order of a 10 to 15% decrease in error. And if you're a wind farm manager or a grid operator trying to blend wind energy into the grid, that's a significant improvement in forecast error. Now, we've also worked on a gridded atmospheric forecast system, graphs. We did this mostly during our solar prediction project that was funded by the Department of Energy. It's very much like diecast. We bring in a host of NWP models, observations that can be specialized on the right. We interpolate to a particular grid. In that case, it was a 4-kilometer CONUS grid, the appropriate averaging period. Then we can apply any number of correction methods. We can use diecast itself at each and every point, and then interpolate on the grid using smart interpolation and blending methods. We've also tested things like gradient boosted regression trees, random forests, analog ensemble methods, etc. Now, that allows us to output maps of the forecast variable. In that case, it was for solar irradiance. We could also take the single point forecast, the percent of clear sky irradiance, etc. This was very useful for predicting distributive solar. We're doing similar work like that now in some of our other projects. Okay, we introduced using machine learning for renewable energy. Let's get into a little bit more detail of how we do that and what folks care about. Now, in around 2009, NCAR began working with Xcel Energy. Xcel Energy is a utility based in Minneapolis, Minnesota, but has service areas across large portions of the United States, including Colorado, Wisconsin, Texas, multiple areas. They were the utility that first reached the larger percentages of wind power. And they found that it was difficult to integrate that type of wind power into their grid, use it smartly without having an optimized forecast system. They had previously been using just NWP output from the national centers. But they came to NCAR, and we spent a few years developing a best practice system for them that we've been continually updating and working with some partners. Now, you'll see that, again, we use a lot of data from wind farms, from the national centers. We run an internal WRF system when we're doing it ourselves. But when you look at our system, many of the pieces of it, the ones outlined in red, are AI methods, with the centerpiece being DICAST, Dynamic Integrated Forecast System, that I just talked about. But then we also use lots of other things. Expert systems for nowcasting have been tested, developing AI systems for extreme weather events, doing solar energy forecasts, predicting potential power, data mining for estimating their load. We've done that as well. And wind to energy conversions. They care about the power, not just the wind speed. They also want a probabilistic, and we use an AI method for that I'll talk about. Now, Xcel Energy, of course, is doing this to save their customers money. And you know, when we started this project, the state of the art from standard NWP forecasts was about 17%. By the time the system was delivered in 2014, the error was about 10%. That's a 40% improvement. And Xcel Energy calculates that it has saved their customers at least $60 million by that time. They've updated it a few times since then and really find that it saves their customers about $10 million per year. But in addition, because they're more optimally integrating renewable energy, they're also saving CO2. And in 2014, that was on the order of 267,000 tons of CO2 saved by having an optimized forecast that predicts better than standard models. So this results in real savings and real savings of CO2 as well. Now, I want to talk a little bit about solar power forecasting. Here in the Research Applications Lab of NCAR, we spent a few years from about 2012 to 2016 developing best practices for solar power forecasting funded by US DOE. And the issue here is to make the best use of renewable energy, utilities need to know when to forecast it. On clear days, as seen in the top plot, okay, the global horizontal irradiance is the red. The power output from a concentrated PV farm is the blue. On a clear day, it's relatively predictable. However, on a cloudy day, as seen below, it can vary quite a bit. So if they need to be able to use this most efficiently, on a day-ahead basis, they allocate their units and plan what they're going to be running. Hours ahead, they need to integrate into the grid in real time. So they need the situational awareness as well as a day-ahead forecast. So that means we need to optimize forecasting for aerosols and clouds. You know, clouds are very hard to predict in some cases. NCAR built the sun forecast, the sun system. It blends the best of numerical weather prediction, where we built a new version of WRF Solar as part of this project that does better at predicting clouds, aerosols, with the goal being to get better prediction of global horizontal irradiance for the use of PV plants, as well as direct normal irradiance, which is the most relevant predictor for concentrated solar plants. Now, in addition to just predicting radiation through clouds, of course, we have this diffuse irradiance as well that depends largely on the cloud droplets and the aerosols as well. So it's a very hard problem. We had lots of team members, including other national labs, NOAA, universities, and we developed a full state-of-the-art system to predict both for day ahead, as seen on the top, as well as the nowcasting system for the next 6 hours we optimized. Day ahead was based on diecast, which I've already talked about. The nowcast system we based on observations in the field from total sky imagers. Brookhaven National Lab did that part. At NCAR, we built a system called Statcast that I'll talk a little bit more about. The day ahead and the nowcast versions were merged. After predicting global horizontal radiance, again, translating that to power prediction, which is what the end user needs, and then to get probabilistic information using another AI method, analog ensemble, that I'll talk a little bit more about in a moment. Okay, what is this Statcast? Well, it didn't take too long into the project and looking at our data to realize that there are big differences between clear, partly cloudy, and cloudy days. We have different regimes. Some of those are based on cloud types. Some of them are based on weather systems that come through. This plot that I'm showing, the green curve is the is the irradiance that hits the top of the atmosphere. The blue curve is data from NREL, National Renewable Energy Lab in Golden, Colorado. That's the amount observed on a typical clear day. This is averaged over the course of a year, data taken at NREL. A partly cloudy day in Colorado typically begins relatively clear, but then it's not unusual to have clouds develop during the afternoon, which is why we see the decrease in irradiance in the afternoon. And then cloudy days, which there aren't that many in a database in Colorado, greatly reduced. So when we look at this, we can see that if we can separate these types of regimes in smart ways, we might be able to develop a smart method. Now, we used standard techniques, but we put them together in innovative ways. This work was mostly accomplished by Tyler McCandless at the time, where our baseline in this case is a clearness index persistence. Okay, a clearness index measures the amount of irradiance that reaches the surface divided by the amount that is at the top of the atmosphere. So it's the percent of the irradiance that gets through. Now, our baseline assumes there is a persistence of clearness index so that we get the change with time of day. It was important to change to this variable. We found that way we were able to take out the diurnal and the seasonal cycle so that we could really focus on the variables that we wanted to forecast. We have equations for the diurnal and the seasonal cycles that we can start with. So baseline clearness index persistence. Then we also look at having a neural network using all data that predicts a clearness index, easy to translate back to the GHI that hits the atmosphere. But we can also look at classifying into regimes using a k-means clustering algorithm before sending to the neural net so that we're able to separately train these independent regimes. So when we cluster, we ended up finding that there were discernible clusters where when we plot the clusters in phase space, they kind of made sense, even though we had done the clustering totally using a k-means clustering method. And when we looked at the results, first of all, the artificial neural network showed a 13.7% improvement over the persistence. But when we classified into regimes, we gained another 5%. Now, how this works depends on how much data you have. In this case, at one of our sites in New York, we had lots of great data, but some of the sites where we don't have as much data, it's hard to be able to train these independent neural networks. So what do we do in that case? Well, another alternate method is to use tree-based methods. I think you heard a little bit on Monday about how random forests work, how these tree-based methods basically are classifiers that learn separation. So this is essentially an implicit way of discerning those regimes. We used the cubist algorithm. It's a rule-based algorithm that uses linear regression at the final node after lots of separation. And then it basically does an ensemble prediction, and it includes some boosting. So we tested that against gradient boosted regression and random forest. Okay, Sue Detling is currently using Cubist in our Kuwait project for solar prediction. For the DOE project, on our data from various sites, when we looked at which methods were best over the next 6 hours, comparing that to our clearness index persistence in black, we find that over the shortest ranges, the Statcast using Cubist really was quite good, the pink curve. And in fact, for the first half hour, it was definitely best, but the only thing rivaling it beyond that was what we called Cirracast. It's a satellite-based method developed by colleagues at Colorado State University. But it continued to beat the best NWP out to about an hour. And again, we found that it depended on the amount of data for training. As Sue Detling is applying this now in our Kuwait project, comparing to a persistence, a clearness index persistence, again, the red curve in the left plot, also comparing to diecast on the very short range, the blue curve, and we find the Cubist, the purple curve, does show large improvement. And in fact, on the right, she has calculated the percent improvement over Statcast over diecast at beginning with on the order of 50%, but then of course decreasing in time as we then hand it off to diecast, which does better over longer periods. But we are able to use these methods to make significant improvements on the shortest range. Now, as I mentioned, the end user, the grid operator, doesn't really care about global horizontal radiance. They care about power output. So we can build power curves where we're able to convert the environmental parameter, the irradiance, to power. On the left, you see a scatter plot. You see it's rather complex. It depends on the site, but when we separate this by time of day and train power, Gary Wiener has been leading some of this research, we see it's pretty typical to get a very good match with errors on the power conversion only on the order of about 2%. As I mentioned before, the end user also wants a probabilistic forecast. They want to quantify the uncertainty, especially on those partly cloudy days when they want to know whether they need to have combined cycle gas units at the ready when solar power drops. Now, of course, the traditional way to make probabilistic forecasts is to run large ensembles of models, but that's not the only way. We can also apply machine learning in this case, where in methods developed by Luca Della Monica and Stefano Alessandrini at NCAR, we've been developed the analog ensemble, which we often use in these projects. What the analog ensemble does, again, beginning with large numbers of historical forecasts on the order of a year or so, we look for the forecasts which have the closest match to today's forecast, the most analogous forecast. But because they're historical, we have the verifying observation. So we can use that verifying observation as a predictor for the period we're trying to predict. But we can form multiple closest predictions, and the observations then can form an ensemble themselves. And we find that the analog ensemble, when we take the mean, it can correct even on our best forecast, even if that is die-cast. Here, the analog ensemble is the dotted yellow curve, die-cast is the red, and we're finding that the correction is better. But because we have multiple observations, we form this ensemble, we can also draw error bars. There's been, Luca and Stefano have written many papers, including with colleagues, and they found that these methods verify as well in reliability as some of the best ensembles being used. And we find that when we look at biases, if we start with the NWP bias, in this case we're solar, it's greatly reduced by analog ensembles. Stefano's recently done some analysis both with bias correction and without. Bias correction can help in some cases, especially where we're looking at extreme events. Okay, at this point, let's move on to some severe weather examples, beginning with prediction of wildland fires. At NCAR, we've had a project for the last 5 years to develop wildland fire prediction methods for the state of Colorado. And we've developed better NWP models to do that, where the fire directly impacts the weather in addition to the weather impacting the movement of the fire. But we need input to those models. And one of the important inputs is the fuel moisture content. And the modeling system is very sensitive to how we use the fuel moisture content. The fuel moisture content is typically derived from observation sites throughout the United States, as seen in this bottom panel. There are observation sites, but those are done by people physically going out there. So it's only done very rarely and updated very rarely. What if we're able to use satellite data and update that using MODIS reflectance bands 1 to 7? We also bring in information from the WRF Hydro model that is the national water model. This WRF Hydro developed originally at NCAR, but now being run operationally at NOAA. And also bring information about surface characteristics, things like elevation, slope, both east-west, north-south, regional information. Throw that into machine learning methods, looking at various different type methods, random forests, neural network, gradient boosted trees, multiple linear regression, looking at both, comparing to both dead fuel moisture content, live fuel moisture content, and bringing in data from both the Aqua and the Terra satellite. For dead fuel moisture, testing each of these methods for for error and finding that the random forest does best. Find similarly for live fuel moisture. Live fuel moisture inherently has larger errors, but we're still able to reduce that error through using machine learning, and in particular, the random forest. So what this allows us to do is to replace the maps that are solely from these observation sites with a gridded product based on satellite data and machine learning for both dead fuel moisture and live fuel moisture. That can make a big difference in the model output. For instance, when we're estimating dead fuel moisture in a particular area. This is a case study of the Cold Springs fire in Colorado. The dead fuel moisture content estimate that was the baseline was 8%. But we found that when we used the satellite-based product, it was actually quite variable over the site. And the orange on the constant side we see is the development of the fire in the model. And when we use the dead fuel moisture percentages from the machine learning, we found that the fire developed quite a bit larger. So there was a larger burn increase. Now the NWP model does overestimate. We do not include fire suppression at this time. So we consider it a good thing to see this increase in estimate because the firefighters want that conservative estimate. So it has made a major project. This part of the project was funded by NASA, accomplished by Tyler McCandless, Branko Kosovich, and Bill Petsky. Okay, one other area of severe weather research, actually accomplished by David John Gagnier, our host today for this meeting as part of his postdoctoral research. And he was looking at hail prediction as part of his project. What he was trying to do is calculate the probability of hail greater than 25 millimeters, where his input was 4-kilometer radar reflectivity. And in this case, for training purposes and assessment, he was using radar reflectivity as derived from WRF model outruns using the NCAR WRF ensemble on days when there were severe weather. Of course, using a convolutional neural network. You heard more about those yesterday. I'm not going to go into detail here. Note he used ReLU, which again was talked about yesterday. But one of the novel pieces here is not only did he look at doing a better prediction, he wanted to interpret what that meant. What type of storm would produce a probability of hail greater than 25 millimeters. So of course, there's this forward prediction given a storm patch. Is it a hailstorm greater than 25 millimeters or not? But in addition, using a back propagation method to update the input image so that he could derive what types of storms are likely to produce hail. Now, I'm in between two methods, two talks here, where you heard about convolutional nets yesterday. Tomorrow, Amy McGovern is going to talk in more detail about these back propagation methods and how they lead to interpretable machine learning. The results of David John's work really are quite astounding, and I'd like to point them out. On the top, we have one example of a particular type of storm that produced significant hail. We have the 500, the upper level, 500 H-Pascal plot on the left, 700 in the middle, 850 or lower level on the right. When we look at what we're seeing here in terms of geopotential anomaly, winds, dew point, temperature, we see what we would expect. We get confluent moist air below, upward motion, and strong lapse rates. And when you look at the wind vector, there's shear where it's almost westerly at the upper levels and a but southeasterly at the lower levels. That shear is producing the types of storms for hail. Now, even more interesting, a different model, number 29, on the bottom, we see this dipole pattern. Again, we have confluent air, but we have two streams of upward motion. We end up with grapple seeding at the top, and doggone if this doesn't match a mechanism published by Heimsfeld back in 1980 that we call the feeder-seeder mechanism. So this backpropagation method, we were able to identify this complex dipole pattern that can produce large hail. Now, when you use these convolutional nets, it allows you to make a more skilled hail prediction. It allows you to encode the type of features of a storm that are going to produce that. And also, it allows internal representation that could enable a more sophisticated way of looking at these large weather and climate data patterns. For more details, look at David John's paper that came out last year. While we're on deep learning, I think because we're pointing toward the future, I want to highlight one aspect of deep learning that I personally, as somebody who's done forecasting over a lifetime, find really exciting. One of the issues that we've always had, we know how to do bias correction. We've used machine learning for that before, but now that we're using these deep learning methods that work on gridded data beautifully, we're also able to do phase corrections. And as an example, I'm going to use this work by Will Chapman, a PhD student at Scripps, and his advisors, where they were trying to come up with better prediction methods for atmospheric rivers. And the proxy, the variable is integrated water vapor transport, IVT. The baseline is a MERA reanalysis that they're using for training. The predictor is the NOAA real-time global forecast system output. Their atmospheric rivers convolutional neural net can produce, can then modify the GFS output to be more realistic and in closer agreement with the MERA reanalysis that is the observed baseline. What I think is exciting is when you look at the difference plots. What the convolutional net has really done is it's moved and reshaped this atmospheric river, the IVT, where we see that there is a correction in both the shape. When we're looking at at the error in the original GFS, a huge phase error, but we're able to correct that and have something much more realistic. I think this is an example of where we're going in the future and what is possible. And many of you out there, I'm sure, are working on similar problems. I'd really love to converse with you about some of those. Now, before I finish, we've been talking about using AI machine learning either as post-processing or in the Wildland fire case as a pre-processing, making the variables the input to the NWP better. But can we improve the NWP models themselves? And as mentioned before, the NWP models are a combination of dynamics and parameterizations, where we get the physics parameterized. And one of the physics parameterizations used is a surface layer parameterization, where we need to parameterize the energy transfer from the atmosphere to the land surface and back and forth. And the traditional way of doing this is using Monin-Ubikoff similarity theory. Okay, so it basically is an empirical method where we know there's certain relationships between variables, but we don't know the coefficients. So the coefficients for MO theory have traditionally been derived from experiments. And most of those experiments have been over flat terrain grasslands. That's not representative of everywhere on Earth, of course, where we have a lot of different types of terrains and large amounts being water-based. So what we want to derive are these stability functions. We want to do that using machine learning instead of using MO similarity theory. So began by getting data from two towers, the Kaba Tower in the Netherlands and an FDR tower in Idaho in the US. And we fit a random forest, tested both random forest and neural nets so that we could predict friction velocity, sensible heat flux, and latent heat flux. So the equations for these friction velocity, heat flux, latent heat flux, here are on the right. They depend on three variables: the friction velocity, the temperature scale, theta star, and moisture scale, Q star. So those are the variables we want to predict so that we can derive the output prediction. Now, at both towers, we had various information on temperature gradients, mixing ratios, wind speed, Richardson number, zenith angle was an important variable, bringing in all the right variables, training the neural nets. Now, I'd like you to notice here, right in the middle, we have what was predicted by Monanubikov theory. We're looking here at temperature scale, the upper set of plots, moisture scale, the bottom set of plots. In each case, we're plotting the moisture scale as derived versus the observed. So, obviously we want it to be closest to the 1,1 line, but it's most telling to look at the R squared, which we want to be close to 1, and the MAE, which we want to decrease. We see that the random forest on the left has made a huge difference. So has the neural net on the right for both the temperature scale and the moisture scale. So it's consistently out-predicting Monanubikov similarity theory, even for these flat terrain cases. Real success for machine learning. Now, when we look at it in table form, again, this in terms of random forest at this point, we are doing a better prediction at the site for the friction, temperature, and moisture scale. But what's really interesting is when we take the random forest trained at Kaba and apply it to the Idaho data, we're still outperforming. And similarly for the random forest trained on Idaho compared to the Kaba. So what this shows is that we can use these machine learning methods to derive parameterizations for our NWP model that outperform the theoretical versions that had empirical coefficients before. And that's even true when it's applied at a site different. So in summary, I want to point out that machine learning really is advancing applications of weather forecasting. It's being used by the national centers, research being done at NCAR, the commercial companies when they apply best practices. Forecasting for many applications always includes machine learning now. NCAR's been doing research in the field for several decades now. It really is a big data, Internet of Things application. It's not at all new. We've been doing it for 20 years. Terminology might have been derived in the last few years, but the methodology certainly has been happening. Again, in weather forecasting, I think we've been ahead of the game. It's become that it's a necessary component for best practices systems to include machine learning. And we saw from some of the examples, interpretable deep learning may be the future, showing lots of promise. We'll hear more about that from some of the other talks. To do a best practice system, we need to blend AI with the physics so that we can advance applications of weather forecasting by using a systems approach, using high performance computing, and using machine learning in addition to the physics. So thank you. I'll go to Q&A now. Okay, I'm looking at some of the Slido questions. One question is, how are the weights of models determined in diecast? Okay, as mentioned in that part of the talk, the weights are optimized. So by having historical data on both the forecasts as well as the observations, we know where the models have biases. So we've already done the dynamic MOS correction as they go into the system that combines the various models. Now, the model basically uses something like what could be described as a gradient descent. But as always, and whether in machine learning methods or in statistical methods, the key to doing a best job is writing a smart cost function. So we use more than the variable that we're trying to predict. We form vectors of variables, and we look at the very specific time. But the basic method is very similar to a gradient descent that has been traditional. It's really the multi-part system, bringing it together, writing a very smart cost function, and doing all this in real time and dynamically updating both the weights and the bias corrections is what makes diecast work so well. It's a complex system, and it's always being updated by software engineers. Okay, it looks like another one that's come up is, why does a random forest do better than other machine learning methods for fire weather forecasting? Is this something to do with the architecture? Okay, this is, I'm conjecturing here. But one thing I like about the tree-based methods is, as I talked about, they inherently find different regimes. And in weather forecasting, we know that, we do have these different regimes. We learned about that over in time, when we have passage of weather systems, we end up with different type regimes. I think that's true in a lot of areas. Now, when we think in terms of chaos theory, attractors, there's multiple attractors to these nonlinear dynamical systems. And I like to picture it as the tree-based methods are finding those attractors and building prediction systems inherently for each of those separate attractors. In much the same way we did explicit regime identification as part of our solar project so that we could get the specific cloud regimes, the tree-based methods are doing that implicitly. In a recent paper written with Tyler McCandless and Sue Detling, we looked at the comparison of the explicit and the implicit methods. And unless you have large amounts of data, the implicit methods, the tree-based methods, really do quite well. So random forest is not the only thing. Gradient boosted regression, the cubist system, they all do that implicit regression. Is there an AI system for hurricanes? And if so, can you give an example? Yes, there's multiple AI systems. I suspect, Chris Rosoff at NCAR is one of the people who has built multiple systems. One system I would like to highlight is using the analog ensemble for hurricanes. Now, for hurricanes, there's, we want to improve prediction of both the track, where the hurricane is going, and the intensity. The analog ensemble was applied to hurricane prediction a few years ago and found that it was able to improve prediction of both. Now, if you look at NOAA's website, I don't know if Jeb is going to talk about this at all anymore, There have been multiple methods tried. Analog ensemble is one of them, but there's been a hurricane forecast improvement system project that has worked to improve hurricane prediction. So that certainly is one thing. In light of talks from the past 2 days, why is that specific mix of techniques gradient boosted in the solar forecast? Okay, for the solar prediction system, first of all, we were developing it between 2012 and 2016. Second of all, we were at that time emphasizing point-based prediction. So at the time we were developing for point-based prediction, really the traditional methods have been better. We have not yet at NCAR tried convolutional nets on solar gridded forecasts. We would love to do that in the future. I think that might be a good approach. Deep learning could make a difference for that. And that could be something that is useful to do. Okay, how can machine learning be used to increase accuracy of forecasts generated by WRF-ARW? Okay, great question, and that's kind of what I've been talking about. You've seen that I've been talking about post-processing of numerical weather prediction forecasts. And at NCAR, when we're building systems, we often use a specific configuration of WRF-ARW that has been optimized for the particular variable at the particular locations we want to predict. So it's already a good NWP model. But then if we do the post-processing, whether it be using diecast or whether it be using some standalone machine learning methods, especially for the short time ranges, we do find that it does increase the accuracy. I pointed out how much does it increase accuracy? By on the order of 10 to 15% for diecast for day ahead forecasts. We can get up to 50% improvement on the very short range using some of the statistical forecasting methods. And in addition, diecast actually does excellent on the very short ranges too. One advantage of diecast is we use something we call forward error correction. Because we're bringing observations from the field, we know what the solution, what the prediction is now. So we make sure we blend any forecast into current. We use that as the current and then blend it into forecast in the future. Okay, Karthik, I see you've come up now.
Yeah, I think we'll still have time to take more questions at the panel discussion this afternoon. I'm sure this is a very hot topic, so there'll be a lot more questions coming in. But thank you very much, Sue, for that great talk. And we'll take a short break for 5 minutes and be back for the next talk. Thank you.
Thank you.